For the first problem that we worked on in groups, we have how many leather and jean jackets should be made to maximize weekly profits. So this question helps me set up my problem. I need to know the number of jean jackets as well as the number of leather jackets that I can make in order to maximize weekly profits. So profits, based on the two types of jackets we're selling, would be $20 per jean jacket and $50 per leather jacket. So we have some constraints such that stitches can make at most 40 jean jackets. So X cannot go over 40. They can make 60 leather jackets at most. So that would be Y is less than or equal to 60. It takes somebody, a worker, 10 hours to make jean jackets. So 10 hours per jean jacket. And 5 hours per leather jacket. And they cannot exceed 500 hours of work per week. So we've included all of the given information from the problem. We did how many jackets, we did hours to work on the jackets, and we have the profit information in our objective function. But don't forget the assumed pieces, like the number of jackets, has to be positive, so it needs to be 0 or more. When we go to graph the problem, we're going to need to know the labels of our axes, which comes from defining your variables. So our x-axis is representing how many jean jackets are being produced, and the y is how many leather jackets. They've already provided a scale for us, but using the inequalities, you could determine that you need something that can include 40, 60, 50 divided by your coefficients here to get your intercepts, and then we have 0, which is just really the x and y axis. So for the first line that I'm going to graph from the constraints, I need x is less than or equal to 40. So I'm going to use a solid line because of the equal to, and when x is 40, it's a vertical line. So this represents when x is always 40, and I want to stay less than or equal. So that means I'm going to be shading to the left of this line. For the next one, we have that y is less than or equal to 60. So now I need to find where the y value is 60 and create the horizontal line to show y is always at 60, but it can also be less than that. So I begin shading, and I realize it's overlapping down here in this little corner from 0 to 40 on the x and 0 to 60 on the y. So I'm not going to bother shading any further to the right because I can't use it later on. I need the overlaps for the feasible region, which we also know as the solution region. So I could also actually clean up the shading from left of x is less than or equal to 40, since I won't need that area either. It's not going to overlap with the red. All right, so we're going to move on to the third inequality, and I'll use blue for that one. To graph this one, you need your x-intercepts. So if I set the x equal to 500, 10x equals 500, then I know that x equals 50. So that's where the x-intercept will be. I can do the same thing to find the y-intercept. This time the x is worth 0 or it's gone. So 5y equals 500. Y is at 100. So I would have to go down 100 and over 50 to get from my y-intercept to my x-intercept. So 100 over 50, moving down, would be a -2 slope. Since the scales of my x and y axes both go by tens, they're the same scalar changes, then I can go ahead and use boxes as -2. So down 2 and over 1. But I want to make sure I point out all of these other points on the graph in case they're my vertices. So I don't want to just estimate where the line is running through. It's also a solid line because we had the equals to on the inequality. If I test the point, since it involves two variables, I could test 0, 0. So I would be asking myself, is 0 less than or equal to 500? And yes, it is. So I want to shade toward 0, 0, which is underneath this blue line. But I'm only going to go ahead and shade where I know it's going to overlap with the green and the red. And this allows me to get rid of some of my shading again. So the red and green that were above the blue line aren't needed because I'm not going to be able to use that information as the solution region or the feasible region. So right now, it looks like we are constricted to this piece of the graph. But we still have to consider our last two inequalities before we just assume we're done. If x is greater than or equal to 0, it would be our y-axis. This is where x is 0, and it would be shaded over to the right. And if y is greater than or equal to 0, it's shaded up. So we are in a good spot here, where I can see all of this overlap happening. And I'm going to mark in my vertices of that feasible region. If it helps, you can remove the lines that didn't fall into the feasible region. I didn't outline it. So we're going to point out each of the vertices as we evaluate the objective function. So for P, I'm going to evaluate at 0, 0, which hopefully we've gotten used to the fact that given our functions, that's always going to turn out as 0. So this would profit $0 because you wouldn't be making any products. But we're also going to need to evaluate the profit when we make 40 jean jackets and 0 leather jackets. The profit when we make, what was another verse? 40 jean jackets and 20 leather jackets. Profit for 20 jean jackets and 60 leather. And finally, the profit of no jean jackets and 60 leather. So I went ahead and solved for the first three evaluations. So if I don't make anything, I make 0 money. If I make 40 of the jean jackets only, I'll make $800. And then 40 jeans, 20 leather gives me $1,800. So if I plug in 20 for X and 60 for Y, I'm going to make $3,400 in profits. And if I don't make any of the jean jackets, so 0 for X, 60 of the leather jackets, I'm going to make $3,000. So our goal was to maximize the profit, and that would be $3,400. That's the largest option. So now we can state our conclusion, which needs to involve information about the company, what they're making, and how much profit they'll have. So Stitches can earn a maximum profit of $3,400 if they make 20 jean jackets, that was our X, and 60 leather jackets, which came from the Y value. So we have our final conclusion made based on all the information that was defined as variables, written as an objective function, written as inequalities for constraints, then graphed and evaluated at those vertices.